So let me just get started. I have a little introduction, just informational things to talk about. But first off, I'd like to thank everyone for coming out to our second AEC Tech Symposium. We decided to do it last year sort of as an experiment, and given the response and all the interest in what everyone's doing in the industry, how we can share ideas, we decided to do it again. And it's a little bit bigger this time, a little bit different. We have the hackathon as well this weekend, which I'll go over. So here are some of the speakers that will be here today. We have a really strong list of incredible speakers and engineers, architects, technicians, computer scientists, et cetera, to share their ideas and what they're working on. Today is the sort of agenda. And we do have a sort of cramped schedule, so I'm going to try to make this brief. All this information is in your handout today, so you can check that out or check it online. This weekend, we're going to do the hackathon, and you haven't signed up for that, please do. It should be interesting. We're going to make some of that information public once it's all sort of wrapped up. And then, again, back to the Wi-Fi issue. So you can check out the information here on our website, core.thorntontomasetti.com, as well as our Twitter account. Please feel free to tweet as you wish. And obviously, thanks to all our sponsors. We try to make this event a little bigger, a little better this year, and we wouldn't have been able to do it without the generous donations from our sponsors. So please speak to them today, talk to them, see what they're up to, and yeah, just check them out what they're doing. So my little short discussion today, my short little introduction, is called Symbiosis, and what that sort of relates to is, the fact is, in our industry, we are nothing without each other, in a way. There's no famous architect that can do their thing without a great engineer. You can't have a great project without a really great team. And so what that involves is, obviously, is really smart people, really smart data, as we'll talk about today, and sort of really smart decisions. And in my opinion, probably, I would say at least 20% of what we do is wasted energy, wasted time, wasted redo of things that we've done in the past. And if we can just harness some of that information from our really smart people in the industry, whether through data sets or through algorithms, I think we could really improve the industry. So this is our typical sort of organization, where we have these little boxes of silos of groups. Different, the architect obviously leads the design process, with the owner sort of involved. Different engineers doing their thing, and obviously the contractor, many times completely disparate from the process. So even within that, we have a lot of personalities, a lot of different skill sets, and to me, at least from my perspective, this is what I see as the challenge of big data, is getting the information from all these people really smartly into our buildings. Now, there's a certain tension that is inherently derived in our industry, in the business of AEC, and that is, we have these really good things, really smart people dispersed throughout, through the architects and the engineers and contractors. But we have this inherent sort of tension of competition. We sometimes don't want to share the ideas because, we think we're better, we think we do things better. Everyone wants to be independent. We do it our way, our way's better. But meanwhile, they keep all that information into themselves. And so, as an industry, we suffer from that. So I think the idea of big data is to capture that data, harness the really smart information, and therefore we can actually have much better buildings because of that. This is the typical process. So there's a lot of things that goes into a building, and the case study that I'm going to show is a small project, but it sort of outlines the complexities of designing a really nice project. So this is what it is, you know, design changes, memos and meetings and all this stuff that we do. And meanwhile, really, there's only little pieces of it that really gets followed through into the project. And so to me, this is what I see is the importance of this, of our industry, is of capturing the data. That's really important. Sorting the data, sorting the decisions that are really smart into the final project. And of course, there's sort of just the data mining process of, you know, what if we can build in, you know, building design, programmatic layouts? What if we can design, you know, building codes into our process? That's sort of, to me, it's challenging, but it's easily obtainable, which we sort of do every day. You'll see some of the interoperability stuff that our office does, and so that's sort of easy, in my opinion. So the hard part is to capture, you know, sort of the war stories, what I'm calling the Sharpie-wielding gurus of our office. And we have 800 people in our office, or 800 plus, but really it's probably only, you know, a dozen people who really have been through, you know, battles and wars and really successful projects, but all that information is buried in their mind, right? So, you know, if you can take any one of these people, you know, like Tom, our chairman, or Anya, our vice chairman, they can get you probably a schematic design in like 2 hours, right? But our young engineers have no idea. And, you know, with 800 people, it's very difficult for the information in these people's minds to get passed down to our young engineers. And so whether that's through data sets, whether that's through algorithms, whatever, I think this is our biggest challenge. How do we pass down the information from the greatest people in the industry down to our people? In the perfect world, this is what it would be, right? We would take Tom Scarangello, who's done, you know, probably 30 or 40 stadiums, multiple high-rise buildings. We create a little component, right? Even if it's just stories, right? Even if it's just data sets, that information is super valuable for a project. I mean, he can tell you, you know, if you have an 18,000 seat, you know, sports stadium, you know, with a hardscape roof, you know, it's going to be 25 pounds a square foot roof. It needs to be, you know, 40 to 50 foot structural depth. You know, all of that information is sort of buried in his mind. We need to just get it out. So this little case study that I'm going to do is a project that we worked on with Joe Scafidio, Renfro. It's sort of almost completely finished. It was a really challenging project because it was really small, but, you know, sometimes really small projects are really challenging. And so this is just to showcase some of the complexities and some of that data, whether it be, you know, just his historical data or institutional data that really went into this project to make it successful. So this is the project. It's really just a trellis or pavilion. It's going to grow plants eventually. But the challenge was we needed to keep the structural members really small. But you can see the scale of it is very large. It's probably some places it's over 20 feet long. The members that form out the walls, as we call it, some of them are like almost 40 feet long. And we were stuck with using most members that are like 1.25 inches. So any structural engineers out there, 1.25 inches is like sometimes, you know, that page is ripped out of the book. You know what I mean? So this is a recent webcam shot of the project. And it was really challenging. We inherited the project from an engineer. The engineer had 2.5-inch members throughout the whole project. So we had to get it back. We had to sort of reel it back into reality. Really tricky details, you know, and I think it's going to be a really nice project once the plants actually start growing on this. So this is a little historical sort of fact sheet of the project. And so, you know, we had many people. This $1 million project, 1.6 million if you include a little like Shake Shack type restaurant in the project. But, you know, so I brought on Kevin Lagenza in our Kansas City office. He was the engineer for the helical bridge in Singapore. The Westchester Memorial that I worked on, you know, we had that sort of really high-end eigenvalue buckling capability, which allowed us to design with really small members. A lot of the detailing was from, again, past experiences, past projects, and this was stuff that, the contractor said, I want to do it a different way. I can't do it that way, whatever. So we had to, like, on the fly, which is why you see hand sketches, on the fly make changes to the design and make sure it was buildable, right off the bat. I'm showing, John worked on this canopy in Oklahoma for Sand Ridge with Rogers Marble, which was like this huge 80-foot cantilever, and we use these thick plate material. So I harnessed that information, put it on our drawings, because we already went through the process of how do we deal with plate-type structures. And it's, this project has these sort of tripod plated masts. And then we had our people in our skin group doing some of the cable analysis. We had Silverio, who's also in our skin group, doing SolidWorks for sort of our sequencing and some of our solid modeling. And then we had Jonathan and Nick and Ann Watkins deriving the grasshopper model, because we did sort of a pre-rationalization of the cables using Kangaroo, and we also delivered the 3D model to the contractors, so we gave them all the work points for the project. And then the project management part, what made it really simple for me, anyway, to have a really direct, honest conversation with the architect was that I worked with Anthony on the Lincoln Center Juilliard project. So it was really simple. We had a really simple, easy-flowing dialogue. Didn't always go that simply, or that sometimes there are arguments and things, but that's what goes through into a really challenging project. And so I'm sort of stealing here from I don't know if you guys remember, but New Jersey used to be like New Jersey and you happy together or something like that. But I'm a New Jersey guy. But this is the way I see how our industry needs to be. We need to share the ideas. We need to harness the really smart information from the really smart people. And to me, that's where we're going to have a really nice project. So with that, I'm going to introduce our first group, which is Dan Segraves and Mostapha Roudsari. Thanks again for being here.
Now it's warp speed. All right, here we go. Our definition, this is sort of a simple, like, we were thinking of a playful overview to set up the talks and be the first one. So as a definition, I'm thinking of data-driven. I mean, it sort of speaks for itself, but data is a sort of aggregate of information and applying that directly to the modeling process. But everyone here knows what we mean by it.
Yeah, we started actually talking about data-driven design, and as you can guess, we couldn't agree 100%. So then we said, okay, we think this is what we call data-driven design. When you have some data coming from some sort of analysis, and then gets to the design, you use that for evaluation, and you optimize the design based on that.
Yeah. So we were going through these bullet points on pitfalls and opportunities, and we'll show some project work for the opportunities, but it's a little bit sort of broad spectrum. Know your problem, which is we often find people solving the wrong problem simply because that's what they know, as in if you have a hammer, everything looks like a nail, that sort of thing. Like, everyone loves to do shading optimization, but sometimes you just apply that to the wrong building, like if you're in Hong Kong or in Anchorage or something where it doesn't matter nearly as much, just because those are the buttons you know how to press, right? Say with natural ventilation. And we have lots of examples of those ones, but that's maybe too negative to show them.
So this picture but we trust your imagination. So you know this picture, right?
This is a classic, and maybe and everyone I think is guilty of this, and certainly we are. We wouldn't have learned how to do things if we weren't guilty of this, which is not using available resources, starting from scratch. It's a good way to learn, but there's also a point where you have to sort of know where to pull from and build up, and there's more that you can learn even after building on what's already existing, right?
Yeah, when you hear people saying these three, usually you are in this problem. Some of them say, I don't trust what is available. Usually the older people say that. But the younger, more creative people usually get to the next two. They say like, oh, whatever, I want to make my own, or I just do it because it's really fun. So, and then you end up being in situations like the next one.
Yeah, just a funny example. We found this. Some blogger was made these up, but it's funny. So new programmer, it's okay to learn the things, though this is not necessarily the best way to do it. But like you often see people starting from scratch, like this would be the kind of enterprise version, where just to get a factorial, you have write all these classes and whatever. It's just ridiculous.
Basically, I love the word standard mathematics system dot.
Yeah.
That's what happens in many of the problems that we want to solve. We start from the standard mathematical something. We do so many high-rise buildings. We start from every time from zero, and we talk about why. But how we should do it is.
Do I have a mouse?
Yeah, you do.
This is my favorite part. If you guys want to nerd out for a second, that he makes the standard mathematics system and it calls mathematics system, which is up here, which is an abstract, which like doesn't do anything anyways. But like the smart person, someone who knows what the resources are, you call the library and it's done already for you. Why rewrite it? But we appreciate you have to learn it as well. But it's there. Maybe you'll start from scratch the first part.
Yeah, I think like one of the main issues that we have there is we so far what we have, usually people, they're not available, some of the data. Then the data that are available usually are not, people have a hard time to trust it because it's not usually open. And then you get the last part that you can't even customize it. When you get it, it's not open, then you can customize it. So it's not really what you need. It's something that somebody else developed for something. And I think a solution for that is now we get with all these open source developments and more transparent developments happening shoulder to shoulder. I call it collaborative development, and by that I don't mean bunch of coders sit together, develop something, but how users and developers work together, and I'll show that. So these are the open source projects that I'm personally working on. They're Ladybug, Honeybee, and Butterfly, for the ones who probably know. There are plugins for Grasshopper. Ladybug does weather data analysis mainly. Honeybee is for daylighting and energy simulation. And then after I developed Honeybee, I met the guys from FreePulse project who are here and based on top of Honeybee, we could develop some stuff to connect Grasshopper to OpenFOAM, which we call it Butterfly for CFD simulation. And then having this stuff, now we have our new friend, Grizzly Bear, coming in. When there's a Honeybee, there should be a Grizzly Bear for GBXML, and Shensi is there. Shensi developed that. So I'm talking about this process of starting something, sharing it with people open source, having it there, and how other people are starting like making on top of that. And then it basically starts to change the way the development goes. Now it's not like I develop for people and then they use it. The users are part of the whole development. And we have so many examples on the discussion forum. I took the latest one, which is here, that shows you like how a person starts from a question and changes to a kind of a developer. So Claudio came there, like he's doing a PhD at Italy, and he said, hey, I need IES materials for radiance. Can you do it in Honeybee? And then I said, it's April 13th. And then I said that day afternoon, well, I don't know. I'm not an expert in lighting. I do daylighting, but it's possible. And then I couldn't stop myself, definitely. So I did it. I said, here you go, but I'm testing. I'm not sure if it works. Next one, I said, OK, I did it and I tested it. But you know what? I don't have other software to validate this. Just validate it if you want to use it. And then he goes and comes back, hey, I did validate it. Maximum difference 8%, minimum difference is 1%. Like, you got it. But this is not the end of the story. He comes back later and says, you know what? Actually, I modified the code. This should be this should be that. You know, this person didn't change to a full developer, but now he feels like part of a development team. This is something he was during the process. He knows what happened to it. He has the code. He can see the code. He can modify the code. He can tell me you were wrong. You know? And this is something that we were missing before. Like this relationship between developers, designers, and there is not something that I think you need. You know what you need. I help you to make it yourself. And we don't even get only technical recommendation. We have like this, Michalina told me basically, Honeybee is not yellow, stupid. I mean, I learned. We changed it. It was yellow. Honeybee is not yellow, for your information. I didn't know that. And then as a result, like this is a graph I took from Brian Ringley. I don't know where he is. Thank you, Brian. So he showed, I went to a presentation this week, and he showed this as 7 deadly sins in computational design, something like that. And one of the slides was this, and he was talking about like how they had to connect all this stuff, which are amazing programs, but they couldn't customize inside the code or something, and they were not interoperable together. But now, having all these people, if you go to the next slide, and he showed this one as an example, like how they had to get that geometries, because Energy Plus can't take Windows as a full surface. They should offset it all, and how was the pain that was, and like what they had to do. So now how that thing works is this. You just do it all, because you have all these things. You have the great Open Studio people developing for you, and they have a good API, and then you know the design, you know the Rhino Grasshopper, you develop as a designer, you just solve all that problems inside so people can go to the next level. You know, this is what I'm talking about, the new way of development, what I call a collaborative development. And you know, this is now getting as important as, I love this package manager for Dynamo. This is basically telling us sharing, and they have a post for the sharing is caring, and it is just great. Like, because they understood the value of people who are doing different stuff, and they can share it, and they made a package manager for that. If you don't know, like in Dynamo, when you develop something new and Node, it just they just take care of everything. You can share it for the whole world just with a single click. And this is amazing. And that's why we have the hackathon. If you haven't registered, you still have time. That's where you get all these people sharing all this idea and all this stuff.
Yeah. One of my favorite. This is hanging in the wall of my mechanic. This, which is so classic. It's so perfect. Which is like, well, the problem that you see in our community is you often see people making these softwares that claim to make it super simple. You don't have to learn anything new. You can just press a button and you get your solution. And I think our point, and Mostapha is very strongly about this point, is you can't oversimplify the problem. You have to know something. You have to have some control of the process at least. And certainly don't trust the things that are the simple button. Except my dream has always been to make this.
Yeah, I have a different solution usually.
And Mostapha's is this. I still like the way this one looks better, but so there's a sweet spot though of having enough control but not too complicated. It's like this mixture between sort of Apple and Microsoft. If you take too much out, you don't have enough input and control of the process. You add too much and it's too cumbersome for any user to use, because it's a user issue as well for all these. So, having worked in the architectural community as well, you always see this, and this is a kind of common cultural problem where the designer isn't used to giving up control of the design. I feel like there's a slight shift culturally that's like becoming more acceptable, or as optimization and computation becomes more common, that this is understood that there has to be some room, but normally it's like the designer can't give up too much control of the design, and at the same time the algorithm is sort of inflexible in that it only gives one answer, and it's hard to kind of combine the two. You like the designers are from ours? And part of that problem is also that you have the coder or the computation guy in a kind of bubble in the black box thing, and it's separated from the actual process.
Yeah, we are doing so much to integrate the process, but at the end of the day, like it's partially coming from the softwares and tools and the environments that we have for computational design. Is like it always ends up to, and I know like many of you guys here are that guy in the office who is the computational guy doing all this stuff, and the design team goes like this, you go like this. When you meet together, you're talking about different projects, and like the other stuff that like you're running something and they come in and say like, okay, you're optimizing this, what is the best solution? And you're like, can you come in 2 days? In the next generation, I will tell you, it's not converged. So this is the work that I have done when I was working at Adrian Smith Gordon Gill's architecture, and we were running this optimization. So instead of just having everything happening in computer, I had another algorithm to print out the best result for every generation. So we could pin it on the wall, and then we had conversations. And you can see all that notes. I don't know if you can see, and all that. So they were like, oh, this is good, or this is that. And they started to learn from the process. It wasn't like running optimization to get this is the wrong answer, this is the right answer, and you're wrong. But it was kind of making a conversation between optimization and computers and people and designers. So the next diagram basically shows the ideal world that we are getting close of, like having a loop with computers and having the experts there being included in the optimization process. And platypus that Ben and Jonathan are going to talk about will help this process so much.
And I thought the other point about this was designers are starting to realize that just a little wiggle room in the design doesn't reduce the intent, and it also allows for often much greater efficiencies in something like, let's say, optimizing a facade or something like that. And along those lines is not only are they in a sort of black box, but they're also, the analysis often gets left behind, as in the design process is moving so fast that the analysis can't make a meaningful effect on it. And it's somewhat partly because of expectations. We need it faster. Why can't we have it right away? And also, you know, that's another cultural thing that has to happen where you sort of you learn to integrate into the process, and the design process accommodates the analysis. But at the same time, analysis are getting faster, and well.
Yeah, this is my first optimization thing that I put something on a computer lab, and I say it takes 151 hours. Don't touch this system for 6 days and 3 hours. So
but these things are getting
this
faster.
is how it used to be. We have one more minute. But then these are kind of a solution that we suggest, having all that problem and being through all that, like not sharing, doing all the stuff, like taking forever. So how we can solve it, we call this remote solving. And basically the idea is when you have new tools, you have new design processes. It's not only about developing the tools, using it in a way that you used to use it. We have new tools, we have new processes. And the way it works is basically we remotely solve the problem for the designers. In this example, they wanted to have these photos, and based on that, they wanted to have their pattern, and they want to know how daylighting works. So instead of telling them, like, okay, give us 10 options, we will run it for you, we set up this system that they could upload their images. Our system was looking for that. It was running the analysis, and it was giving a meaningful report to them. And it was basically, we changed it to a game that they could test their ideas more and more. And it was running on our system, so we could take care of the speed and all that stuff. So it was a good collaboration. They could do what they really want to do. We could take care of the analysis, the speed, and the accuracy, and everybody was happy, kind of. And then I don't know, did we ask them? Are they happy? I don't know. I think so. Okay.
And then a sort of closing two, which are a little more moral. This is sort of about scientific empiricism, where you often do these analysis just to sort of validate what you already thought. But you see the skewing happen a lot. But this is kind of, we're asking you to stay empirical, because you know this is true.
Yeah. We don't know if it's bad news or good news, but it's real.
And then everybody knows this kind of problem as well.
Yeah, like if you go back, this is the most important thing. Just use the data for the right reason. Don't use it for the wrong. Data for data's sake, wrong. Because it's trendy, don't use it. And because we can do it, it doesn't mean we should do it. It doesn't mean we can do modeling, rendering. Now we can do analysis, we should do it. No. And I love this quote. Like, yeah, you just read it. Can you read it? Yeah, I mean, like, use computation, but don't stop talking about it. Your project is that. And then if you end up with potatoes, Enclos is gray. That's it. Like Mark Gay from Yale. And yeah, like this is, we don't have time, so we go fast. So here is, they call it hype cycle. And it's about technology. When a technology trigger, everybody's just like, yeah, this is amazing. We solved all the problems of the world. Then you can't, boom, then you go down. We almost never go this way up to get here. And we are in that loop. And you can locate yourself. And what we want to do is just to push it to the plateau of productivity. All this sharing stuff, all this teaching, all this remote solving, everything is just like, we don't want people to come to this place and say, oh, it's useless. Boom, next pick. And then what is missing here?
Now, the one thing when we're talking about data is we're actually missing the discussion of big data. Big data doesn't really play a part in design so much in the way that we're talking about, is in the data-driven part. I mean, you see it in medicine, or in this case, it's Larry Page dreaming about medicine, but we don't have a good standard, and we don't have a good aggregate of building information of existing. We don't learn from the buildings, which would be the sort of, I think, the first place where you'd see big data starting to play a real role in actual design process. So it's sort of a question for, can we use it in buildings?
Yeah, and you haven't wake up, so this is the yellow one for you. That's it.
Thanks. So we have Jeff Vaglio from Enclos.
Well, good morning. I'd like to first thank TT for the opportunity to speak to you this morning. I work for Enclos Corp, Advanced Technology Studio out of Los Angeles, and we are a facade subcontractor. So my presentation today is going to talk a little bit about actually constructing in the field, how the tool is carried from estimating, which is the first time we touch it, develop that tool, carry through structural analysis, and deliver on site, and how the tool is useful when all that data you generated, goes out the window when something's off in the field. So, this started off as a project that there are 952 unique panels on, and I didn't want to draw 952 unique panels. So I said, how can I draw a logic that allows me to do that? And so I started to use Grasshopper on this project, but this slide is important because over the course of 4 or 5 years, the Grasshopper model was then touched by other people in our organization, estimating, a structural engineer on the production end, a visualization guy, and a field crew. So really, one thing that our group focuses on is process. The project always changes. How can we use process as our practice, study that, refine that from time? And process to us has input and it has output, and how we handle it in between is really the big question. So the project I'm speaking to you about today is the Fulton Street Transit Center down in Lower Manhattan. And this is a collaboration. This is an MTA project. The part I'm talking about is a Jamie Carpenter art installation structure within a Grimshaw project. Eric was involved in it, and then we partnered with Tri-Pyramid to source some of our componentry on the job, as well as Durlam for some metal panels. This is an interior view of the transit center looking up through what is termed the solar reflector shell. And this has 952 unique panels. It's controlled by over 1,000 XYZ coordinates, and all for just 8,500 square feet. So this is, in our eyes, a small-scale project. It has metal panels, not glass, so it's a forgiving structure. And so we thought this was, 5 years ago, this was a good project to apply Grasshopper as much through the process as we could. This is a section through the building. I'm going to go through some of this stuff because the meat and potatoes is really at the end of the presentation here. But there's a superstructure of V columns that hold up a shell that is clad in metal panel, and then within the shell is this doubly curved surface that's hung from the oculus at the top. This oculus at the top is angled to allow daylight in, is reflected off these metal panels, and allows light to go deeper into the public realm of the station than what is maybe usual in a transit facility. This is about a little over 2 years ago, under construction. The structure was closed off at that point in time, so the net was hung inside not for another 18 months or so after this. It was hung about May last year. So the oculus has a ring beam at the top. This net is hung with a series of 56 paired cables, and then it is tensioned down at the bottom into shape at a series of catwalk levels. The componentry, even though every panel is different, the componentry within the system is universal connectors. So this is a typical detail, and this is funny because there are no typical conditions. This never occurs on the job. Everyone is skewed or pivots around this hinge point here. And this is a photo from an outdoor mock-up we did. And the whole idea here was, from the very beginning, we said, how can we deliver this to the site in one piece and hang it in one pass and just pull down at the bottom to introduce the tension and achieve the final geometry that was the target form. And so the focus was going to be at the bottom, how do we connect this last rod, how do we tension that and achieve the desired look? So mock-up was a big part of this process. Here's an example of the componentry that was used, the universal connector, pivots around here, stainless steel cables in both directions, in 2 different planes offset from one another. And ultimately, here's a tri-pyramid mock-up very early on in the process. And this is cool. Each paddle was indexed to where its location, its address within the project was. Every panel had an address that was engraved in it as well. So the way we used Grasshopper was first, this is how we received our data, which is a series of X, Y, Z points. But it wasn't that easy. And then the idea was, how can we use these points to find a way to automate the panel generation? So the obligatory routine shots. And then here, it's really a question of what happens when you're not in control of the data that's going into your process. And this is a position that we're in all the time. So during estimating, the way we received data was on 24 by 36 drawings that we then had to scan and perform an OCR text recognition, put it into Excel, and then have an intern quality control it. Because 1s and 7s confuse themselves with one another. And ultimately, we set up a database, an Excel database of XYZ data that was then going to be the foundation of everything we did from that point on. It's going to be the foundation of structural engineering, of all the geometry automation. So we used Excel to manage the points. We streamed it into Grasshopper. We used Rhino to visualize. We used Grasshopper to do, first, all our takeoffs and all our takeoffs, lengths, quantities. And then ultimately, we export that data back into Excel and create a series of tools that our sales team can use, or we can supply to vendors, the non-sexy stuff that gets the job built. The next step is we get the project, and we say, well, how can we really maximize what we have using this? So the way we receive the data, once again, within the net, the data that is critical for structural analysis is the pretension within the net itself. The way we received that was these tension values sort of as bands throughout the geometry at its certain tiers. Well, the reality is the second you impose those loads on the structure, they shift. The structure is going to distribute those loads the way they want. So really, you end up with a new set of information that is each node and each cable segment has its own pretension that it needs to achieve for the form to achieve its final shape. So we went through a series of structural analysis routines to try to find the right values that we would use at the bottom to pull the net down to achieve that desired distribution within the net. And more or less, it took about 4 iterations before the structural model converged on what was required for the tolerance that we would be held to in the field. So in this case, we took the Excel, we took it into a structural analysis tool. We evaluated the deflected shape. If it met the desired tolerance, then we moved on. It didn't at first, so we had to create this feedback loop and ultimately create a new geometry. So all those data points we lifted off the 24 by 36 are now replaced by a new set of structurally driven data. Now, the real merit of our intention was in automating the geometry of the panels. And the way that was done is each panel is controlled by 4 nodes, creating a quadrant. Between the center lines of these nodes, there's an offset that creates the bounds of the panel. Then each panel is folded. It's a metal panel, it's perforated, and it has sort of a perforation along the back that allows it to bend in the field. So it's very flexible. And that's what allows these 2 triangles to be non-planar but of one element. So what we had to do within the 3D model was take out a panel that is folded in 3D space, orient it so it was coplanar, and create the pattern cuts that we were then going to source to our metal panel fabricator. So this is what that looks like. We have all 952 panels over here, but really that's not the format we exchange the information with our vendors. This is one of the pitfalls, is that a lot of times we're not contractually able to just hand over that information and check models. So the way the metal panels were done on this project, Durlam out of Germany did their own model, and then what we did was we compared Excel data sets from one next to the other. So these are the informations that controlled those, and we ended up with more or less a black and white canvas doing our quality control. So prototyping is a big part of what we do. These processes, trying to convince an organization, a builder, that using Grasshopper is a good idea, not just for design, but throughout the entirety of the delivery process, has its struggles. So what we did was we first beta tested this on a small scale. This is a mock-up that we did in Massachusetts at Tri-Pyramid Shop. We did all the structural process, all the geometry stuff in this exercise. This is the actual cable net. I like this shot because this is like a literal visual of a grasshopper routine. You have all the spaghetti strands, you have all the nodes, and really it's this mess. But in the end, it ends up doing something really beautiful and creating a form in the field. So this is a video of a practice installation we did in Massachusetts. Practice lift. Now the whole idea was we want to lift this as one piece, deliver it to the site as one piece, and then give it shape in the field. And this was not easy. This is a test where we're completely outdoors and there's no constraints of things around. The reality is on the job site there's that metal-clad shell that all this had to be lifted within. And there are obstacles that had to be avoided. So there's a choreography that had to take place with this lift. And this whole development of how the strategy would be installed was developed not by just a designer or an engineer. It was developed by the field crew, the superintendent, who was going to be responsible in the end for doing that. I'm going to breeze through this quick. I'm getting the 5-minute sign here. But the point here is, how do we set up the tool to flex when the data in the field goes wrong? And when the primary structure was put in place, what we learned was it was off ±2 inches in pretty much every direction. And what we were going to be held to was a geometry within this net that we knew going into was going to be out of place. And so what we did was we waited to fabricate the rods at the bottom until we had that survey data, made our adjustments, and then just fabricated the 56 rods that were at the base to the appropriate length to make up for those issues. The legibility of the structure that we were going to be held to by the designer was really going to be the gap between the metal panels, between the cables. It was going to be a qualitative survey in some respects rather than getting back to the finite XYZ coordinates of things. So things always go wrong in the field. One of the issues was we hung the net and it looked like when we were going to hang the metal panels, these were going to be in the way. Well, there's a clash detection done, there's an exchange of models, and it was said, no, nothing's wrong, there's no clash. Well, let's go old school here, and let's just cut this down and look at it in 2D. And what you realize is in 3D, the diffusers weren't modeled, right? So the diffuser projections were the thing that were going to be the issue. So sometimes you have to not just rely on the 3D or on the parametric tool or on the clash detection, but you have to do the groundwork as well. Okay, so I mean, this is the point that the precision of craftsmanship is really what these complex shapes come down to. We can have finite tables to 3 decimal places, and we can control data all day long. But the reality is when something arrives on site and it's loose or somebody's measuring with a measuring tape and a pencil, that's the reality. I mean, the tool isn't going to build it on its own. So you need these people to understand the tool. You need to relay the information in a manner to them. So this is a shot with the panels partially installed, and this is about 4 minutes, so don't kill me here. But this is kind of the whole story. So what we think of the model as is a narrative on how we construct the project in the end. Yes, Grasshopper helped us through estimating. Yes, it helped us through structural analysis. Yes, it helped us through the fabrication and quality control. But where it really helped us was telling the story to those who would be installing the net, how this would go down. Labor is expensive in New York. We want to minimize that as much as possible. So this whole idea of the net arriving on site, one piece, maybe have a 3-4 times the size of the crew you would normally, but get it done within 4 hours. Get this thing hung between 7 a.m. and lunchtime. And so this, we had to work with the superintendent. We had to work with the GC on site and say, listen, we need sort of special clearance on this day to do it, and we had to do it right. It's a one-time shot, so that's why we practice it up in Massachusetts first. What you see here is the delivery of the net, the Grasshopper routine all bundled up. You see there's some interferences within the dome. There's a stainless steel-clad stairwell that has a drape over it that we'll see in some of these shots, that the net had to be lifted up at a very steep angle and then tilted into the right place to avoid damaging this already finished piece. That elevator, or that stairwell, is what we see here. So this is all both a study of storytelling, but it's a study of geometry. Is this lift going to be able to work and get that clearance that we need on site? And so the way this was done was a temporary ring was created out of a series of 8 different segments. It was bolted together, and sequentially the net started to peel onto this temporary structure, unravel, and gradually be lifted. so this went down the way it was intended. It was hung in a matter of 4 or 5 hours. You see here sort of the sequence. And this was the visual that was used to communicate. This all stems back from the roots, from that Excel data sheet, from that Grasshopper routine. How do you leverage it, when you have a project and when you have to build it? And so much of that is not the empirical data that you can pull out of it, but the constructability issues that you can relay, whether it be addressing field issues or addressing how to construct it. Once the net was hung, all the universal paddles were kind of set, and then the panels were hung. The net was tensioned first down at the bottom. Then we had to have a little more sequence here. So one of the things I've been thinking about recently is this notion of the finite versus craftsmanship. And these tools can really allow us to be as finite as we want in terms of relaying information. But that information is only as good as those interpreting it in the field and those building it and constructing it. So how do we, not simplify, but how do we leverage the best ways to communicate to them and the field knowledge that is required to really optimize this process? If you're not using these tools to build, then we're missing an opportunity. And that's what we're trying to do here. Use the same tools that designers are using to find form. We're trying to use them to resolve the installation of the form itself. Okay, so in summary, we didn't know what our data, we weren't in control of the data. We brought it in, we set up some controls, used it for estimating, structural analysis, fabrication, installation, and mock-up. A series of tools, that was the initial vision. This is the vision of the installation sequence, the reality of that sequence, and the end of the presentation. Thank you.
So we'll do questions at the end with our Q&A panel. Next up we'll have Nick Scalco from SOM New York. Nick, there you are.
All right. Thank you, Daniel. Thank you to TT for having me here to speak. Today I'm here to talk to you about data. Specifically data and how we're using it at SOM to improve our practice. What you see here is a picture of inland steel designed by SOM in Chicago. And you might be familiar with this setup that you see. Basically, it's a host of engineers working at tables, rolling out their drawings and getting to work with some pens and pencils. Much of the data that we produced at this time was all analog, right? So all the knowledge in that data, all that knowledge was implicit in the drawings. When it came to putting together some standards for SOM at that time, you're familiar with the standard, right? Something established by an authority, usually as an example, something to provide a base of support for the rest of the firm. So these standards, they were typically put together by a group of individuals that were very experienced in the firm. They would come together and they would hash out what each of them did on a project, what worked best for them. But there was no empirical knowledge to back that up. It was all anecdotal evidence. They'd sit around the table, say, this worked better for me, this worked better for me, and then the louder voice won. Right? So within this process, we know that there are some things that we're always going to remain to be true. First, that we would embody knowledge to start off from a more advanced point. Also that we would provide mentorship and professional improvement, as well as have the standard benefit all levels, projects, phases, and types. And there are a few things that the standards shouldn't do. Unduly restrict a user, be difficult to understand or manage, or introduce unnecessary effort. So when we came to developing a standard for how we're going to move forward at SOM, our drawings, our specifications, our process has changed. We're no longer using this analog process. Much of what we're producing now, most of what we're producing now, is all in the computer, especially with building information models. These building information models contain a lot of data that we can call for expertise. So as these models evolved, a few people in the office, a few teams in the office, they started off with basically taking the torch, running with it, developing these projects inside of Revit without any standard. And when it came to figuring out how is it that we're going to develop our standards for building information modeling, we could have gone the old route, right, where everybody sits around a table, it's very time intensive, hashes out what's the best method, or we could cull the data that's already implicit in the models themselves by pulling that data out, making it explicit, and giving some actual metrics to back up some decisions and judgments, right? The big data itself, by definition, it's usually beyond the ability to analyze and manage just as an individual, right? And because of this, we wanted to use a tool to do some analysis and aggregation. So we came up with this framework, right? First, we were going to select the Revit projects for review. At the time when we were setting up the standard for Revit, we probably had about a dozen projects in the office. Half of them, or half dozen or so, everybody was very happy and successful, found them to be successful. So we decided we were going to start with those half dozen projects that we were all very happy with, and cull the information out of there with a custom tool produced to basically pull out some metrics and produce some reports. You had that data, you had it as a metric, and you had it in a graph, but the answer wasn't in that graph. The answer was basically sitting over that graph with a group of experts and deciding, with that explicit knowledge, what worked better for which project, and then ultimately document these standards for explicit action. So this is one of the reports that were produced. And as I mentioned, these half dozen projects, they weren't done with any standard, so everybody had their own way of doing something. And this is what you could find out with this report, all the ways that people were doing things, and start to figure out, well, which ways were actually working, which ways were actually better than other ways, and then how could we go about documenting that work, right? Walls are a great example. The walls, when you're doing drawings, you just had a 2D representation of a wall. It's a couple lines. It provides a barrier between spaces. A wall in a building information model has a lot more information associated with it. You have STC ratings, fire ratings, and whatnot. So we wanted to see how were people managing that data inside the models, but also when were they inputting that information. We had models from all phases of the project process. So we had DD models, we had CD models. When was it that people were actually inputting that data, if they were inputting that data at all? Ultimately, after mulling over a lot of those reports, we came up with the final report and a series of recommendations, not just about how you might go naming something, a naming convention, which is something you find in every particular standard, but actual processes that we would use to employ throughout the project process. So these ultimately culminated in a series of documents that we use inside the office. What you see here, this is a screenshot of what we call a container file for enclosure systems, right? So it's not just a 2D document that somebody reads. It's actually a Revit model that somebody can interact with and see, not just actually use the components that are within that model, but processes associated with producing those components as well. And then for a little bit more detailed information, instead of having a book, which was traditionally produced for a standard, we developed the SOM BIM wiki, which could have a bit more detailed information than the container files could hold, but could also evolve with time, and a lot of people could contribute to it as well, as opposed to a 2D book, which is just static. So we got through those tools, and we got through that process of culling the information in historic terms, and we thought, well, what if we wanted to do this on a project that's currently in production? Okay. Ultimately, we're going to look at outliers and patterns. This is the lowest hanging fruit when it comes to analyzing big data. It took a digital design specialist at SOM almost a full week to come up with all this data from one project. Now, if we were doing this through a manual process and the model was actually in production at that time, the model's already out. The model has already moved on once this data has been culled and analyzed. Right? This data is now out of date. So we thought, okay, perhaps what we can do is take that tool that we developed for analyzing or for culling the historic data, evolve it into a Revit add-in, combine it with a web interface, right? Push that out to the web, and then something that can produce reports and everybody can see and react to in real time. And that's what you see here. So we can not only analyze models themselves along with projects, but an aggregate of all the models in the office as a whole. And you can see this chart here. What we have is projects by file size, area, and a number of models. To go through everything inside of all of the networks inside of our office and actually come up with this type of data would take somebody quite a bit amount of time. Now I have it at a glance, and I can see one of the outliers in the far top right, Sheikh Khalifa Medical City. This is a perfect example of using big data to manage consistency on a project. Sheikh Khalifa Medical City, very large project. It's about a little over 3 million square feet. Ultimately, it's around 5-6 hospitals inside the United Arab Emirates, all inside one building. We had to manage, because it's such a large project, we actually had to break up this project into many models. We ultimately had 24 active architecture models on the project, along with another dozen structural models, split between 2 architecture firms over 2 continents, as well as as well as an engineering office in Germany. Very large project, a lot of information, a lot of data to learn from. So anyone who has managed such a large and complex project knows the headache of keeping models, multiple models across a project consistent. And we thought, well, this is going to be a great opportunity to use the BIM dashboard, have it in action, and actually see what it can do. Right here, at a glance, you can see the project. Thank you. See the 5-minute mark. So at a glance, you see Sheikh Khalifa Medical City. Just at a glance, I can tell where a lot of the work is going by model, by file size. I also have the ability to look at how many links per model, as well as the amount of model warnings within each model, all at a glance over the entire project. Just opening up one of these models can take a few minutes. So having this information readily accessible saves a lot of time. And I can drill down into the models themselves, and I can see not only aggregate information about the data stored in those models, unplaced and placed families, the amount of views on sheets versus the amount of sheets. I can also see a trend over time, which is what you see in that large graph in the top, right? That trend over time is telling me that model, as it develops, it's developing steadily at a very steady pace. And that's really beneficial for me to know, because I can tell that model is at least being managed, right? There aren't peaks and valleys. People aren't adding a lot then purging a lot. I can tell just from this graph that things are going pretty well, as well as the graph to the bottom right, kind of cut off in this view, but your warnings as well, which is something we've also harvested from the models. How many warnings per project? I can see here that's trending downward. Also, something that we used from the standards that we developed were the container files. As I mentioned, these were Revit files that contain not just components, but processes. We could copy those files to a project directory and then use the information in there to develop specific components for the project and document those components. So here I'm showing one of the container files that we started with for our walls and how that container file developed over time. All right, so we could eventually document our walls in an efficient manner and make sure that we're producing these walls consistently throughout all the architecture models. Here you can see there's an overview of all the placed components inside of the project. The walls are third from the top. I can actually drill down and see all those placed instances of the walls, see how many I'm using. So ultimately I can make decisions about whether or not a wall type can be merged with another wall type. Maybe I don't need to have 40 different wall types. Maybe I can get away with 30. All right. Something also great about this graph is at the top, casework. You might not know this if you've never worked on a healthcare project. Casework's actually really important for a healthcare project. It's not life-threatening, but it's very important for a project. And that's something that I can see very early on through culling this data that we need to work on managing and placing the casework to ensure consistency. And then ultimately we have what we call the checker changer. And this allows me to compare the information inherent in the components in the container file, our wall container file, to all the other models in the project. So I can compare the container file walls to the walls within the 24 architecture models and make sure that the information inherent in those components is consistent. Sheets are another big headache if you've worked on a set as large as this. Over 9,000 architecture sheets. Keeping those sheets, managing those sheets, where they're located, just in which models, was greatly improved with the use of the SOM dashboard. Here I can create a sheet list, and the dashboard can actually tell me which model the sheets are located in, and also which users those sheets are assigned to. So I know who to talk to, and everybody on the team knows who to talk to about what we're using on the about who's responsible for what on that file. I see I've got only a couple more minutes. Warnings is another one, and as I mentioned earlier, warnings trending down over time. I know that's a good sign. All right, so ultimately we thought, well, what else beyond building information models is producing data inside of our office? And there's a lot more project information beyond the BIM model. So what I have here is now the evolution of the BIM dashboard into the project dashboard. And you see an aggregation of all the projects inside SOM currently across the globe. And we're starting to gather metrics of each of those projects in a very friendly interface, so you can actually compare those projects and the metrics associated with them, so I can start to understand how those typologies that we've worked on previously could inform precedent studies and designs in the future. Things such as FAR, floor plate size versus rent span or lease span. And then actually compare different levels, different floor levels of a project to other floor levels of a project, so we can start to see which designs are working better for certain typologies. Ultimately, the goal here is to take the implicit knowledge that was once just within the files and within the projects themselves and extract that, make it explicit, and allow and basically document that explicit knowledge to allow everybody in the firm to use it. That's it. Thank you.
All right, now we'll hear from our keynote speaker, Shane Burr with Woods Bagot. Shane.
So again, thank you very much for coming. It's a great opportunity for me to catch up with a lot of people I see every once in a while, but these sort of gatherings are fantastic to just catch up on what the current status is of design, engineering, construction technology within the industry. I spend quite a lot of my time both as the Director of Design Technology at Woods Bagot and a Director at Smart Geometry, thinking about how these things end up affecting our daily lives in terms of how we design, how we build, and ultimately experience space. It's been great for me to be able to watch some of the work at Woods Bagot over the last 2.5, almost 3 years I've been there, make their way from these early sort of design iterations, thinking about geometry, thinking about analysis, the ways that this building will ultimately end up performing. And I showed a little bit of this project last year when I had a chance to show off some of Woods Bagot's work. But in the end, this is the sort of thing that gets me excited. It's the physicality, it's the real materials, it's the actual experience of the space. And does it actually perform the way it is? We haven't run a post-occupancy analysis yet, but these are the sort of things that we want to learn. We want to know, how does this actually affect people's productivity within the space, and is it something that they enjoy their experience? Does it allow them to new possibilities in workplace, new possibilities in the sort of environment that they work within? The other part of my job, my Woods Bagot being my day job and Smart Geometry often being my night job, is to work with running conferences every year and workshops centered around bringing these questions about. New themes every year, but ultimately a group of 10 workshops that explore different facets of a topic, all centered around how do we reinvent the way that we work as designers? How do we take advantage of mathematics, algorithms, analysis, or whatever, so that it becomes so intuitive that it's just like working with pen and paper. I mean, this ends up being a multidisciplinary exercise between practice, industry, and academia. But the point is we want to exploit these tools. We want to take advantage of the things that we see in the presentations today and use them to really push our capabilities as the next generation of digital designers. And we do that through active workshops, prototyping, live actual elements that you spend 4 days in full intensive workflow, physical, digital hybrids, experience, build, break, fail, succeed, all of that together as part of that. And the prototyping process is something that I consider to be incredibly important. By the way, for those of you who don't know, workshop applications are due Sunday, so get something in over the next few days if you can. Through seeing what I do at Woods Bagot and what we do within Smart Geometry, I see two camps, I guess, in terms of how we work with design technologies and building technologies. A group of people, which will be well represented by those here today, who view technology from the view of a technician as an aspect of problem solving, as something, this is a way at which I can take in a certain amount of data, whether it's physical data out there in the real world, or the ways at which we want to work with that data to influence the design process. On the other side, which I have a feeling will be less represented here today, is those who see technology as an aesthetic in and of itself, beyond the bounds of reality, a techno-aesthete, somebody who you look at it and that is, well, I guess you would, if you want to use Schumacher's term, it's parametricism to some extent, and the various iterations that occur afterwards. I have utmost respect for both. Each of those are pushing us further down the line in the interactions about how technology influences culture and the culture of technology. But in the end, I'm interested in something quite a bit beyond this. I'm interested in a transcendence of technology where the means at which you use this technology becomes something that's in the background. And the results end up being a lot more subtle. It's technology that enables expression, craft, and experience. The concern I get now is that I'm starting to feel that our ability to have an impact on the design of experience in the built environment is becoming limited within the realms of design and construction technologies. And that's ultimately what I want to spend a little bit of time talking about at the tail end. This talk is a public beta. I'll let everybody know that. This is the first time I've really talked about quite a few of these things. So I greatly appreciate any feedback so I can make it to version 1.1, or actually I guess it'd be arguably 0.1 to 0.2. I don't think it will ever finish, so it'll probably be an eternal beta at some point. I like to look at the use of technology from a conceptual framework. This is fundamentally where I begin. And for me, the viewpoint is always the view of a craftsman. What does a craftsman do with technology? And again, this is referencing all the way back to Malcolm McCullough's Digital Craft book. It's Richard Sennett's book on craft. There's a number of different views on how craft works and how we integrate the tools, and it becomes an influential part of our process. In terms of craft, you can see three basic exercises occurring: exploration, technical execution, and ultimately delivery. And each of these will have a parallel all the way into computation, into BIM, into everything that we end up doing. For me, that kind of settles down within design technology as the relationship between sketches and prototypes. Sketches as being a very simple one-dimensional or maybe two-dimensional, but a limited set of exploring a particular design idea, and it doesn't necessarily need to have permanence. Whereas a prototype, we're looking for some level of multi-objective optimization, collections of information combined together to solve multiple goals and give you a much more persistent set of information that you work with. I've never been a fan of the term BIM. I'm sure quite a few others here may feel the exact same way. For me, it is prototyping. BIM is too limiting of a term. BIM is a subset of the entire sketch and prototype process. And for me, prototyping, the word prototyping is more evocative of a step in the process towards the realization of the design itself. There are four primary kinds of prototypes, and this is consistent across industrial design and other types of arenas. You've got aesthetic or form prototypes, so whether that's a 3D model that you've built in your in the computer or however method you've actually gone about it. There's functional prototypes. You may look at BIM as being one of those because we've added functional requirements to the model. It has additional information. You have experiential prototypes. What is it like to use the object? What is it like to be in the space? In industrial design, you would 3D print it out of multiple materials. You'd physically use it and see how the kids break it, however you want to work with it. What is experiential prototype for architects? That's a good question. Last being proof of concept. We saw some of that from Enclos before with the Fulton Street Transit Center, the physical mock-ups, the proof that this does work, this will become what it is. I do think we lack an appropriate mechanism prototype mechanism for fully experiential prototypes. Is it game engines? Is it animations? Maybe. I'll come back to that in just a little bit. What I want to do is walk through a couple of things that I'm seeing within the design and construction industry in terms of technology. We're going to hear a lot more about this over the next few hours. We already heard some about it before, so I'm deliberately not going to repeat. Although I did warn some people on Twitter a few weeks ago that I was going to cover topics so that they didn't have anything to talk about later. I'm going to try to avoid doing that. So at least for Daniel Davis and Randy and a few others in here, you can relax a little bit. I won't cover your area. At the very beginning, you have got both design, computation, and BIM, and the eventual merging of these into a cohesive process. It's very simple to see why that would be appropriate, because both ultimately deal with the flow of data from concept to construction to occupation. You don't want a separated process. The only reason why it's been separated is from purely software point of view. There's no fundamental reason why we should do that. You can work in a database, you can exchange information back and forth. We don't have to deal with just geometry anymore. We can deal with representation and abstraction. In the end of that, the goal of this is that the BIM process or prototyping process increases its ability to handle complex geometries and analytical workflows. Conversely, computation starts to preserve and increase its relevance to the life cycle of design process through that level of integration. Other aspects of the kind of digital workflow from a design perspective are what we saw early this morning when it came to data-driven design processes. And I think Randy will probably come up a little bit about how you use big data in that process to inform what you do from the early stages all the way into the realization of the project. And then ultimately in the end, we bring all this stuff together into multi-objective data optimization processes. So these are things where we can look at all the different factors that combine in the design process and start weighing the comparisons. It's interesting, I had an opportunity to see some work being done by Cornell and Stanford a few days ago on life cycle processes and multi-objective optimization. And it's something that I think has been very relevant within, say, aerospace industries, within automotive, within industrial design, has yet to really come to fruition in a lot of architectural design. And ultimately, I think will start to come into a greater degree. Seen this before. This just came up a few weeks ago. China is printing 3D buildings. They did, like 30 of them in a week or something. It took about 24 hours to print the building, although arguably it was printed effectively on the side and then was brought up into the process. So they're printing elements of buildings, not necessarily entire buildings. Now, I've been connected in some way with 3D printing going back to about 2003, 2004. It was the first time I got a chance to play with a Z-Core machine, now 3D Systems machines, but Z-Core then. And they were a lot of fun. They kicked out a lot of dust, but it was great for the prototyping process. You got to look at those aesthetic, those form-driven prototypes to understand, okay, this is what my design is going to become. But after a while, a certain degree, it stops informing the design process. I think probably the best example of I've seen it used in the design process has been coming out of Morphosis, where it is treated very much as if it's a sketch element, as if it's part of something that is sacrificial and modifiable. But I start getting a little bit concerned about our over-reliance on 3D printing as being the ultimate gauge of, yes, this is possible, I can make this. Because until we can actually 3D print the building all the way through and through, it is not a representation of fabrication or construction. So for me, I always take it with a grain of salt. I look at it, I'm excited, it's a lot of fun. I don't own a 3D printer at home because I just don't want that much plastic stuff in my life. But I can see how this is something that's going to eventually go forward. But for me, I always put an asterisk next to it. Oh, I love robots. Everybody loves robots. I see this sort of stuff, a lot of fun. The last few years at Smart Geometry, I've had a lot of fun playing with these, although I have to admit there was this moment last year at the one at the Bartlett where they had 3 robots working in tandem with each other, and there was a discussion about whether a piece of red tape should be drawn on the ground at some point. And the big question was, well, what is that? Well, that's the kill zone. That's if something goes wrong, that's where it's going to hit you and you're probably going to end up dying. So if you make a stupid mistake like translating a positive to a negative integer, the thing's going to fly over and smack you on the ground. That's not the issue. That's not what I'm really concerned about. But again, our fascination with robots is being the answer. This is what's going to solve construction for us. This is going to build everything for us. I have absolutely no trouble with us continuing to look at these processes and look at opportunities through robotics. But to assume it's going to be the answer right now in the next year or two, I think is naive. And I think there's much greater opportunities to look towards how they integrate as part of the process, but not necessarily the answer. And the same degree, I have to say, for drones. Drones are exciting, a lot of fun. I'm probably going to make one at some point or buy one or have a little bit of fun with it. And I think there's definitely opportunities for drones to inform the process. But is architecture and engineering construction really a competition for who uses the most robots and drones for it to be exciting? I don't think it really is. Again, there are appropriate uses for this, and it will eventually get to the point where you can have something pick up and move it over. But in terms of thinking about efficiency and what is the appropriate use of a carrying device and assembly device to put things together, I start to get a little bit nervous about this. It's fun, but are we actually progressing the profession itself? Now, for me, I want to understand construction and fabrication technologies as an opportunity for craft. What design and craft opportunities do these provide to me? What can I learn through the process? What can I take advantage of to accelerate and to push the profession into areas that we haven't gone into before? Not just make it more efficient, but do something entirely new. Are we teaching these new construction technologies in academia as we did before, not as an end in of itself, but as a design and performative responsibility? Technology, for me, combines with what we can see coming in the near horizon is the opportunity for technology and human interaction to increase in terms of how we manage projects on site and how we manage assemblies. This is a shared space system. This is the human plus the technology combined together. For me, it's an augmented aspect of construction, not replacing robots simply for the sake of it. Now, what are some great opportunities for this year? What are some automation? What are some things that we can get out of this? Location and sensing, very obvious opportunities for use of drones and other types of systems. Yes, we can do site surveys now, very similar to from the film Prometheus by using drones. This is, science fiction in the end becomes a wealth of technology narratives that we continue to mine. This one in particular, which should come up in a second here. Maybe some of you have actually seen this project. This was a demo where basically they hooked a sensing device on the very front to record three-dimensional data. It's run 4 times the speed, so it didn't actually run this fast. But you see an opportunity for us to set one of those in, or to look at an overall site, have it continue to take photographs, to sense information and define the space, and to develop that model for you. These are the sorts of things that would be absolutely fantastic to use drone technology for, rather than walking through with a nice expensive like a 3D scanner, take a scan of that space, move to the next one, move to the next one, move to the next one. So there's an opportunity for us to partner with these machines, to use them for what they're ideally suited for. You've also got great things like ShopBot CNC equipment like the HandyBot. How can we augment on-site assembly to deal with site tolerance issues in real-world conditions? This specific project, or this specific element being one where you can go up there with your hand and do a lot of the work, but it's handling all the micro-calibration for you because your hand's not quite as steady as you want to. Again, a technology augmenting the actual construction process. I showed this last year. This is from Smart Geometry 2013. This is the group out of Spain called Modelica, who started looking at digitally augmented construction assembly, using computer vision, using sensing to actually augment the construction process. What they were looking to do was to augment masonry assembly by using people with sensing and calibration and the ability for live modification. This is actually using a Microsoft Kinect to scan the space continually while they're actively working in the space, and the use of QR codes for location and software like OpenCV and Aruco. This takes care of the issue of where we want to start connecting computer vision with the construction process. You're working with the technology. So as you are assembling it, it's providing you additional information live on the site. This is where the next piece should go. Oh, you've got that 1/4 inch off. Why don't you tilt it a little bit up? But then it's also able to continually change. So if something causes the tolerance to go off, it will recalculate and adjust for you to make that change so that by the time you get to the edge of the wall, you're perfectly lined up. These are opportunities for us to actually start mixing technology, computer vision, sensing, location-based information to be able to push our capabilities. Human plus technology and a shared space system. This, for me, is what I see as the next kind of major drive within the construction process on site. Take the best of both worlds. Now, Construction workers are going to be such beautiful people with Google Glass on their face. Can't you just picture this? And they're excited, and it's really happy. It's probably a little more like this. Maybe not exactly like this either. To be honest, it's probably more like this. That is a real website, by the way, whiteguyswearingoculusrifts.tumblr.com. But again, these are opportunities for people to use this type of technology to provide all sorts of additional information that they normally wouldn't have had before. Right now, you've got perfect examples out there in the healthcare industry where doctors are able to walk around with that information and be provided up-to-date information as they're working. Or mechanics be able to look at a car and repair a car and have access to the videos and the current status of that car's performance on the screen in front of their face while they're actually working with their hands. Aerospace industry, all sorts of other industries are taking advantage of these opportunities to provide you live, contextual, on the moment at that realm of information that you need at that exact moment to complete the task. And all while you're doing that, feeding it back to a central database that keeps up to date with the current tasks for the day. This is the type of thing that we would like to enable by handing our BIM, our models, over to a contractor to keep track of scheduling, to keep track of what needs to be done. It's giving up-to-date information in a bi-directional way, but still allows that construction worker to take a step back and hopefully focus on a little bit more craft. For me, the future of construction can be influenced by a lot of different locations. One of them could even be the defense industry. This being an example of the next generation soldier. You know, this is somebody who's got a heads-up display to be able to hand additional information up for the exact context of which they're working with. They've got an exoskeleton to assist with additional physical strength or things that need to be done. I don't know our construction worker is going to have exoskeletons, but there are lots of places where we can pull information from other industries to say, this is how we can start using technology to automate the construction process. What are some of the fundamental technologies, however, that we think are going to be influencing this? You've got good examples of computer vision. This is what a Google self-driving car sees. This is what they understand of the world. You can see some physical data. You can see some semantic data. You've got sensing. You've got location. You've got big data all pulled together. And ultimately, it needs to be understood and contextualized through things like graph databases. So where does this take us to? This gives us opportunities to start looking at smart buildings, smart cities. Zach will talk in a little bit about the kind of city aspect of this work as well. You know, organizations or companies like IBM, Google, Microsoft, lots of different companies are getting involved in the entire smart city movement. And what they want to be able to do is they want to be able to look towards the kind of data that they get. And apologies, this is kind of blown out a bit, but this right here is actually City Bike on September 17th and 18th of last year, from about 6 a.m. all the way through the course of the day. This is how people move through space. This is how they use infrastructure. What can we learn about that? Well, the obvious one is it allow them to move particular bike stations to where they're actually needed. That's a very simple one. But when we add these layers of data out throughout our entire infrastructure, we enable our cities to perform to a much greater degree, and we start noticing patterns, and we start designing for these patterns. We also allow our machines to start understanding our world. This is an example of how the Google car understands how to make a right turn with a stop sign. It visualizes this information as a sequence of steps based upon what's learned about the environment. And then it'll provide you this information in front of your face so that if you're the one driving the car, it'll prevent you from hitting somebody, it'll provide you additional information. In the end, one of the fundamental questions is, well, how is this going to change how we design cities? In a very simplistic way, in 5 years, we're going to have automated cars. How does this change how we design and plan for the urban space that's around us? Smart buildings. Obviously, we've got the Nest, which was purchased by Google, which means they're going to gather all their data and sell it to somebody else or do something with it. But you've got building management systems in general, the ability to map energy use and to drive basic controls of the environment. They're also able to recognize use patterns. So you know that whether or not your child goes up and keeps turning the temperature down when they get home from school, well, then it doesn't need you to do it anymore because it will understand, kid came home from school, I now want to go through and have the system respond in that sort of capacity. This is happening a lot within larger scale buildings. It's happening a lot within homes in a basic degree through Nest and through Birdie and some of the other systems that are out there. This is going to continue to adjust how we actually interact with the space around us. The cost of sensors is also getting incredibly low. This is the MediaTek by Enrique Ruiz-Gelli. There was actually an interesting discussion that he had with a number of technology providers about the costs that would be associated with an activated facade system. In this specific facade, it was wanting to pump nitrogen into these ETFE pillows, which would make them translucent and adjust the light levels and the heat gain that would occur through this facade. Intel was quoting him a price of about 1.5 to 2 million, and then they discovered they could do it all with Arduinos and basic off-the-shelf equipment for less than $5,000. It's a very simple way of looking at this and saying, okay, the cost of sensors is low enough that this becomes ubiquitous. This is becoming something significant. In the end, though, there's a limitation to adaptive buildings. I think there is an over-fascination with adaptive structures. Absolutely beautiful building, really beautiful in terms of how it interacts and what it can actually do with the space, but ultimately I feel like it was too much effort for little impact. An entirely activated facade, which by the way, this specific facade doesn't have any sensors. It doesn't react to the environment around it. It's actually entirely pre-programmed. Now, that works within certain environments, but that's only going to work for a certain number of years at the same time. We're living in a time frame at which, from what I understand, the El Nino effect is going to be incredibly intensive this summer, much more than the last few years. How does that change how our buildings react? Can they dynamically adjust? I'm not so sure. I also think sometimes we have better ways of dealing with microclimates when you're a little bit cold. It's called clothing, and I think clothing works really well. But at the same time, yes, there's room for this. It's all a trade-off as to how much effort you can put into this and whether you're actually getting the benefit out of it. I'm playing devil's advocate here. I love this stuff. It's beautiful. It's fascinating. But put an asterisk next to it. For me, put your time and money where the energy where it will be most effective. Beautiful stuff. How effective is it working? Or does it end up just being much more of an artistic exercise, part of the aesthetic, the techno-aesthetic, rather than the performance itself? And of course, how long does it last and how long does it continue to work? One of our roles as designers and engineers for the built environment is as an integrator. Technology should not just be a flat screen that you put on the wall. For me, technology should allow us to take care of the expectations of the user, to start building flexible work environments, to think about the bring your own device movement that, process that everybody has nowadays. Can we take an opportunity for our buildings to learn from the patterns of use and design in the built environment, and therefore develop rules to generate new programmatic arrangements? This being a system that is used to design a static collection of program, but what if this was dynamic? This is the point where you no longer need signage because your mobile device is going to tell you exactly where you need to go and it's going to know where everybody else needs to go within the building. In the end, personal technologies such as smartphones, fitness trackers, even Siri, personal assistants like Siri, and intelligent thermostats will make a larger impact on our experience of the built environment that we've probably ever seen since the advent of the elevator than car, and much more than arguably some of the things we're even going to be talking about today. Things like the quantified self, the ability to measure your performance, everything about your body. So we went from smart cities to smart buildings and now smart people, I guess. By the way, you can get these for your dog too. Personal assistants, things like Siri, Google Now, Windows Cortana. Good examples, I had a conversation with Ronnie Parsons of Studio Mode about a week or so ago, and one of the comments that he made was he was going to be driving upstate, but Google warned him, leave early because there's traffic. So he left early, started driving up there, and then as he was driving, it told him to take an early exit. So he took the early exit because Google knew that there was bad traffic and then didn't tell him to get back on the interstate until the traffic was bad, was in much better shape. These sort of personal assistants completely affect how you end up experiencing space. But it does come with a little bit of an issue. Is it starting to ruin our ability to understand prediction and have a critical view? Come back to it in just a second. San Francisco, sorry, I said San Francisco because I write SF on my notes. Science fiction, and San Francisco because it has Silicon Valley actually. Science fiction provides many examples of the way that a personal assistant will affect how people work. This being an image from the television show Person of Interest. This is a view of the machine, by the way, which is an AI that has access to security cameras. This is showing what it sees and the way it then affects the actors within the space through little headsets to telling them, do this, do this, do this, do this. Because it is actually directing things for you. It is being in charge of the actions that you take. Ubiquitous computing was a term that was actually brought about, I believe in 1988 was about how far it actually goes back, or sometimes abbreviated as UbiComp. This is a diagram that actually shows this sort of progression from a mainframe to a network to a mobile to the ubiquitous devices. You've got pervasiveness in the Y direction, you've got time in the X direction. So 1960, information technology is born. 1970, computers begin to communicate with each other, the network. 1990, you get the emergence of mobile devices, basic laptops, beginnings of tablets, PDAs. 2000 to 2005, systems start to become ubiquitous. Thermostats, everything having a processor within it. And then beyond 2010 and further, intelligent systems start to become ambient. And this is where we get the term ambient intelligence. 13 billion internet-connected devices in 2013. 13 billion. It's projected to be 50 billion by 2020. This will have a far greater impact on our experience of the built environment than what we design for that same built environment. You look at what Mark Weiser, the chief scientist at Xerox PARC, said. He noted that when he coined the term ubiquitous devices back in 1988, the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are so invisible that they are indistinguishable from it. So the sort of principles that we're looking for in terms of designing of environments like this, and again, this goes back to 1988 in the ubiquitous computing side. The purpose, number one, purpose of a computer is to help you do something else. Number two, the computer is a quiet, invisible servant. Number three, the more you can do by intuition, the smarter you are. The computer should extend your unconscious. And number four, technology should create calm. This is that progression from the individual computer to tangible computing to social computing into embodied interaction. Well, ultimately, the human being, the person, is the center of the experience of that environment. And in the end, that's a phenomenological approach, which we as architects have looked at for decades. The concern I start to get when we look purely at technology is what Scott Smith from a blog called The Changes called flat pack features. These are these perfect features with maximum productivity and zero waste of time. It was interesting, Malcolm McCullough in his latest book, Ambient Commons, notes, does having more ambient information actually help you to notice the world more or less? Or does it just simply lower the resolution of life? The sort of thing I'm concerned about is the lack of agency, the ability to act on your own futures, to base everything on purely task-oriented monoculture. I don't want this to sap your ability to be critical and think independently, or to look ahead and anticipate. What we're starting to experience now is this combination between the physical and digital self as an existing hybrid. We exist in multiple personas because you've got a smartphone in your pocket. You and your virtual self, your physical self, exist in the exact same environment. And despite what we picture when we think of projects like Google Tango, the use case where it will have the most impact will probably be as a technology that enhances physical and digital hybrid environments. Now, this is me. I'm Shane Berger. I'm Director of Design Technology. I'm a Director of Smart Geometry. Yesterday, I was 64.211.192.54. I'm also at Twitter. There's my Woods Bagot email address. I have a web address. Back when I did bulletin boards in the early 1990s, that was my handle. And to my friends, when I was in jazz band, I was Bootsy. I have multiple personas. When you look me up on Google, I'm either the person standing in front of you now, or I'm a South African cricket player. I, in the end, am my network. I'm a graph of relationships. I am my metadata. Considering all that, how do we design for digital natives? Perhaps it's cliche, but I have an almost 6-month-old daughter, and it's given me new perspectives on this front. You've got children touching television, thinking that they can do something with it, or trying to zoom on an image in a magazine. These sort of things are where we start thinking about what is an affordance. How do we deal with affordances and when we think about digital natives and how we think about digital natives within the built environment? iOS 7 is ultimately a response to the fact that people are now very used to already touching glass screens. So you don't need to have knobs and you don't need to have buttons that operate the same way. In terms of other digital natives, you've got Africa as a mobile-only continent. They're skipping mainframes, they skipped personal computers, they skipped tablets, they're mobile-based. This affects how we think about the difference between persistent and adaptive environments, all the data around us and the ability to overlay augmented reality information. This being a kind of close-up of all the sensors that are actually occurring right around the Center for Architecture in central Manhattan. These adaptive environments are rich with data. Dynamic change ends up being the norm, and mobile and computational systems, sensors, location-based systems are ultimately going to drive this. What this is going to mean for us is we're redefining what we mean by space and place. Location and context through networks become the organizing principles. Our connection to a place, our interaction with others, and the meanings that we assign are changing because of ubiquitous computing through mobile devices. The definition of space is no longer permanent. The question, and this is ultimately where I'm getting to, is our traditional definition of architecture becoming obsolete? With smartphones and wearable devices affecting our environment much more than what we think we're designing for them. User experience designers in software industry are doing more to define our human experience than architects and engineers. The interface arts are becoming the prominent arts. I'm going to skip this for 1 second. All right. We are effectively kind of missing the boat on taking advantage of this. Companies like this, Intel, Cisco, Qualcomm, Google, Apple, they're actually calling the shots on what our built environment is going to be like. Our role as architects and engineers should be to understand and forward digital culture through the lens of architecture and urbanism. And as before, the social conditions will drive the future of technology. This future is going to be more weird, diverse, and driven by social issues than you expect. And what it starts to make me ask is, do we need a new kind of pattern language? Our framework for understanding and designing human experience is increasingly obsolete. New kinds of social interaction are mixing the physical and digital. Design thinking is a prized approach in business. We need to re-engage that part of the process. We should be designing for networks of people, networks of interaction. The graph network is key. It's related information, it's contextual information, it's personalized data that will drive social interactions, not necessarily the exact dimensions that Christopher Alexander states should be a sidewalk in relation to a street. That's changing. I'm interested in how then this affects the sketch and prototyping process. We're not just prototyping former space, we prototype experience. We mix together different possible futures, room for improvisation. The group out of Superflux calls this design futurescaping, this being a good example of what the possible new environment for an architect and a designer might actually be. You get examples of how buildings start to operate as platforms, like the work out of MIT Media Lab's Joseph Paradiso and the Responsive Environments Lab. This is connected to the electronic nervous system, buildings that start to act like an extension of your body, like a prosthetic. This becomes a control panel for buildings, and it starts delivering meaningful data, not just purely numbers, but semantic data, something that can be used to help manage the relationships and how you interact with space and work with other people. I'm interested in what they call lossy futures, the minimal amount of information, the relationships that people have to each other that allow you to fill in the gaps yourself, not the flat pack futures that tell you task, 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 and then you go to bed, which of course you've been measured in your sleeping habits during the entire night so you can improve it the next morning. I'm interested in the lossy futures that act much more like how a jazz combo would work together, with the basic chords, the basic melody, and an opportunity to improvise. Now, what do we think is the most appropriate data we should be taking out of BIM to provide this? Is it COBE? No, I'm not so sure that COBE is actually going to provide this kind of information to get you what you want. What should we be looking for? Well, here's the point. Context is key. We should be looking towards opportunities through graph databases, just like Google, just like Facebook, just like all those other groups are looking to interact with people and to design social relationships. Context is necessary to draw meaningful conclusions and actions. Open data standards, because of this, are absolutely essential. You can't have one platform not be able to talk to another platform. Now, in the same way that we pull forward fabrication into the computational design process so we can design for fabrication, how can we pull forward this type of experience to design for it? What is the nature of a sketch, and what is the nature of prototyping and designing for a dynamic experience? Can we take advantage of open source software and low-cost sensors to sketch in code and hardware? Can we look towards gaming engines to help prototype the physical and digital hybrid interactions of space? In the same way that we work to provide FM and COBE data for building management, what kind of data do we provide to enable embodied interactions? If buildings equal data, then who writes and controls the API? The company that controls how we interact with space, this company will control how we interact with space much more than the architect. Should we be prototyping and building and writing the API as part of a new kind of deliverable? If you want to help determine how design technology will have a great impact on a built environment, it's my belief that you need to start telling stories about how these new kind of experiences start to happen. And in the end, don't be afraid if they start sounding like science fiction. For me, the best kind of science fiction, just like architecture, enables us to ask critical questions about social structures and propose an environment they'll all inhabit in the future. Thank you.
If anybody has any questions, you can use one of these mics on either side. Please don't be afraid to step up. Don't make me ask all the questions. Here we go.
So yeah, when it was first developed, it was actually something that a user had to do. So it was a manual process of a user actually selecting that tool inside of Revit and pushing the data to the web interface. That is time intensive still, unfortunately. And we all understood that at the time, but it was the fastest way to actually prototype the tool. Now we actually have a server running the harvester. And what we have on the web interface now is a tool where you can schedule when that model is harvested, right? So you can schedule it for a harvest every day. You can schedule it for a harvest once a week, every month maybe, depending on whether or not the project's very active or not, and how often you want to analyze it. So we understood that that was going to be a big barrier to entry, was having actually people take the time to harvest, and that's why the tool's evolved.
Do you guys envision a future where we just have like Walmart boxes with Oculus glasses and Oculus Rift glass, something where the virtual is the real? I mean, what do you think about that? And maybe if we have driverless cars, does adjacencies and locations, does that even matter at some point? Does this keep you up at night?
It does keep me up at night sometimes. I think the thing that I start to ask questions about is our reference point for virtual environments is physical environments, what we see and what we're used to now. That's what we understand as being up, down, left, and right, hard surfaces, soft surfaces, all that stuff. At a certain point, it's very hard to picture what that means to a digital native, someone who hasn't necessarily encountered that, where the very first thing you do right after they're born is you put a headset on them so they experience a virtual environment instead. I don't know. I find the entire virtual reality thing to be not necessarily the most exciting opportunity, but for me, it's the hybrid environments that are much more exciting to me. It's the overlay. So maybe it's not purely an Oculus Rift because you're blocking your eyes entirely out, but maybe people will be scared of this at some point. And funny enough, back in, I think, 2001, I did my undergraduate thesis on the topic of cybernetics and kind of connections between body and technology. But a heads-up display for most of you might be in your future, or at least your children's future at some point. It's not, it may not look like Google Glass, but it is something that could provide you with extra information that you're not getting out in the environment as well. I think that's a much more rich environment than just saying, you know what, the physical world's not interesting anymore. Let's just go into a Walmart box and put an Oculus on.
I'll ask one more. How about that? I see this discussion seems between Jeff and Shane where you're talking about this kind of naive, pure data making its way to reality. And on Shane's side, you're saying that there's these tools, for instance, augmented construction, that are bringing construction and reality closer to this sort of pure data state. And you're talking about these processes, Jeff's talking about these processes that bring pure and sort of simple data, embedding it with the intelligence of reality. And I feel like there's you're implying that there's some point where these meet. And I'm curious if you thought about like what that is in the future.
One thing that hasn't really been discussed is the separation of trades. And my perspective is, purely based on one trade that's in a sequence of other trades and within a bigger context. So I think there's realities of contractual issues, exchanges of informations, competencies with those informations. I'm biased. I feel we're doing pretty good on our end with that, but we engage every day with people that it is a roadblock with other trades, and so that information flow is obstructed, more or less by the classic construction process that's in place right now.
Yeah, I would agree. I think there's right now the gap that's in between is simply a technology gap to some extent. It's people not necessarily interacting with each other, the same tolerances, the same types of technologies, the way that they want to work. It will at some point probably merge. You won't necessarily need to have these sort of automated calibration systems on site to correct for construction tolerances while you're working, because it would have been prefabricated perfectly off-site and then consistently recalibrated in the fabrication process. But right now the technology is sitting in that zone in between the two. I guess where I start to say, okay, it's no longer just an issue of fixing problems, but an opportunity is then when you do want to look towards opportunities of craftsmanship. You give effectively a design space for the craftsman to work within. So you've given them the parameters, the computational parameters to work within on site based upon the real environment and the general directions to where the design is supposed to go, and they can effectively improvise. So that for me becomes very interesting. So we can still use the kind of pure data environment to set the design space, the craft space that they work within, but when they can then have that ability to go on site and improvise within that with additional data while they're working, that becomes exciting to me. I don't think we've seen that yet.
So you want the human to remain part of the human aspect. All right, so we're going to take a break. Oh, one more question.
This is a question for Shane. Compared to last year, I feel like there's a big difference in your attitude toward the things that have been happening with the AEC industry. But I think what was interesting is a comparison between the AEC industry and the other industries such as software companies or aerospace. I think ultimately the question is they have the amount of resources to invest to create these analysis because what they're selling is reproducible. And in architecture, I think we're handicapped by this notion of having to create unique product every time, in a way. So do you have any opinion on that? And I guess I have another question, maybe a comment or observation is your comparison between this kind of programmed, this parametric architecture to this new way of thinking about architecture with the available technology and embedded technology. Is it in a way a kind of new techno aesthetics in a way, because it's just kind of new, more available tools that's kind of accessible to us. I guess that's two.
Okay, both very good questions. The second one first. For me, it's not a technology aesthetic so much. I still would prefer it to sit in the background as much as possible. It's an enabler for people to interact with each other. Now, granted, when someone goes on Facebook, they get completely absorbed by the fact that they're on Facebook and maybe less about actually talking to the people that are on there. I have a sister-in-law who spends most of her time, I think, playing games because I get all the damn notifications. But that's about, I should shut that off at some point. That's about putting the technology in front of you and being just seduced by the technology itself. I would rather have this sort of ubiquitous computing environment, the kind of ambient technologies, to really push to the background where it's much more about the interaction between the two people. That for me is much more interesting. I guess the other question was, the sort of resources that we run into. I think we have actually an advantage. I think what we have learned through architecture and engineering training is this sort of iterative process, the design thinking process that can allow us to take quite a few leaps over what we may see in other industries who can throw millions of dollars into research and running all sorts of market research and things. I think we can actually do a lot through the kind of sketch prototyping process and make some pretty big leaps and bounds. But by the way, I'm not saying at any point that just because they're doing it and we're missing out on the opportunity that we shouldn't talk to them. We can partner with them. They should be part of the process. We should be buddying up to, well, we're already probably buddied up to Google and everybody because they have all of our information. But you know, these are people we should be partnering with and working with, because the thing is, they're looking out there and they're seeing a gap. They're seeing something not being covered by the people who are supposedly designing for the built environment, and that's us. And they're jumping into it because they're going to make money, and they also have a greater impact on the built environment. We should be in that conversation at the same time. We can partner with them. We can take advantage of their resources, but then also take advantage of our own training and design thinking.
All right, one last one before our break.
Hi, this is a question for the entire panel. The challenge that I've seen with model data extracted from a model is that currently it seems like the effort to either quality control that data on the front end or validate that data on the back end tends to be it tends to not be worth it, is what I'm saying. I actually work in construction and we do a lot of quantity takeoff. So I'm wondering what kind of solutions the panel has seen for that, or what sort of trends you're seeing that may bring about some kind of technological solution, something along those lines.
It's a good question. Speaking from a construction buildability side, I think it will change. I think it's the project manager of the future. Those are tasks that a lot of times a project manager who has gone through a construction management program maybe wasn't as ingrained in the 3D environments. Well, I think it's happening. I think we could do a better job in academia, but maybe the construction managers of the future or the project managers of the future aren't just construction managers. Maybe they're architects who have a knack for that kind of thing. And I think as builders, as general contractors, the vision for what's expected of a project manager in the future who's executing those QA, QC processes is you know, a huge opportunity.
Yeah, so just in relationship to the tool that we've developed at SOM, I think what's important is that the data that we're extracting from the model, right, we're extracting that data through a tool that makes it easier to at least get the data out. And one of the things we're looking into now is what about, once you have extracted that data, right, how do you go about taking the knowledge that we have and evaluating the data and analyzing it and making judgment calls on it, and building that knowledge into some of the processes that are happening on the web interface. So something that we've developed is the idea of like thresholds, where we understand that certain projects of certain sizes should have certain metrics based on previous projects. This is something that we can insert into the actual analysis of the project, and a user is presented with a dialogue saying, hey, you know what? Your warnings for this scale project, your warnings have gotten a little bit out of control. You need to look at these models. But I think that the idea is we're basically automating those processes that the computer can do well. We don't want to extract the human interface, the knowledge and the judgment that goes along with experience from individuals. But we do want to see what of that can we build into the tools.
Can I answer to the question that he asked and left? I know we're standing here between you and coffee, which is not a good position, but I think like not only the resources for the research, but I think the comment that you made about buildings being so different for every single one, well, I think it's so controversial, and we should just walk outside one of that and just look to the buildings. If you don't consider the buildings that we are usually showing in like conferences and all this stuff, which is so unique, I think, like all the other buildings are not that different. And even if you look at the buildings that we are showing here, at the end of the day, I mean, just if I'm talking as a person who does object-oriented programming, and especially in Python, everything is an object, so everything is similar at the end of the day as an object. I think the main issue right now is we don't have that data shared and structured. If we start having it shared and structured, we will see that we have so much in common that we don't have to do over and over. Then I think that research is going to be meaningful because we're researching on a component that can be used over and over for other parties.
All right, thanks guys. Let's take a 15-minute break. We'll come back on our second session of design, data-driven design.